All right, let's take a look at the Module 9 problem set. And I want to show you a way to solve this that my professors would have considered cheating. But future generations are going to say, well, of course you do this. So let's see how to solve this with a computer. This is a more useful skill in the long run than doing it, by hand with pen and paper. Of course, pen and paper gets you there, and in some cases that is the appropriate tool for the job, but learning how to get your computer to do math for you is how you're going to be able to do genuine statistical work. If you want to be a Wall Street analyst, this is a skill that you're going to need. The pen and paper aspect is part of the understanding, but getting the computer to do it is another skill on top of it. So let's look at this. Now, off the bat, I'm getting not great, that's what I'm looking for. It's not properly formatting the equations here. So I'm going to be relying on my sheet of paper over here, but let's just read this. So left parenthesis x, right parenthesis space equals. Okay, f left x, right parenthesis. So this is just f of x equals. That's really annoying, but let's go ahead and write that out. Now here, I've kind of given this away in the Discord, is running a derivative of a derivative for question 5. But we'll build up to that. So f of x equals 9x squared. Okay, well that is easy. This caret sign, shift 6, is how we denote an exponent when we're typing math. So 9x squared plus 4x. Let's put some spaces in there just to make it a little easier to read. Plus 4x minus 20. So if we just put that into Wolfram Alpha and hit enter, it's going to show us stuff, right? So here's hopefully what you were seeing on your computer. On mine in Firefox, it worked last week. It's not working this week. Such is life. This typed math is harder visually, but like I said, getting it into the computer, well, that's going to come with its own problems, which is the computer doesn't look at the whole thing. It looks at it one character at a time. So we've got the function itself. We've got a picture of the function. The questions we're asking are, what is, does it give us the derivative? Look at that. It gives us the derivative even also. So the questions we are asking is find the derivative, find the second derivative, find the slope at x equals 1, and tell me the sign of the second derivative is what this last part is. Is the slope getting steeper or not? So this is a good simple example to start with. We can see at 1 it is positive slope, right? So whatever our answer for that part should be a positive number. And it looks like it's getting bigger also. So our second derivative should have a positive sign. So we can ask Wolfram, derive this function. Differentiate. All right, so it figured out what I wanted. Wolfram is pretty good at that. So I didn't even have to really know how to ask the command. Other programming languages, you have to be much clearer, but Wolfram Alpha is built with an emphasis on making it easy to kind of just jam stuff in and try things out. So we've got a result. Our derivative is 18x plus 4, or same thing, 2 times 9x plus 2. That is the derivative of this. So we bring the 2 down, right, and that gives us our 18x. We bring the x to the power of 1, becomes 1 times 4 times x to the power of 0, which is just 4, and then minus 20 goes to 0. Right? So our derivative rules, it's a pretty easy derivative to do. So then we can plug in 18x plus 4, and that'll give us the derivative of the derivative. It's just 18. And that was pretty easy. Another thing we can do is differentiate the derivative. So here we've got our original function. Let's try this twice. Differentiate. And I'm going to try one more thing. No. All right. Let's try putting it in parentheses. So hopefully it interprets, figure out what's in the parentheses, and then differentiate that. Okay, well, can't win them all. So that, just like before, 18x plus 4. So here is our second derivative. And then we can ask, what is the slope at x equals 1? What is the change in the slope? And our result is 18. What that is telling us is that at this point in our original function, let's go back to here, at x equals 1, the derivative of the derivative is 18. So let's plot the derivative of f of x. And here we can see our derivative was 18 plus 4, or 18x plus 4, something like that. 18x plus 4, it was exactly that. So this is what's going on with the slope of the underlying function. So if we go back to our function, we've got a parabola, and that parabola has a slope of less than 0 to the left of this value of x. So when x is about negative 0.2, that is when we have a downward sloping curve. At that negative 0.2, we flatten out, and then we switch to having a positive curve, and the whole time it's increasing. So we start with a very big negative number that becomes a small negative number, right? So if you think about my arm representing possible values up and down, we've got 0 here, and then we can think below sea level and above sea level. So our slope starts way below sea level, big negative numbers, small negative numbers, hit 0, small positive numbers, big positive numbers. And that's exactly what we've got with a parabola. Right? So when we want to know what is the slope at x equals 1, now we can take this derivative. I'm going to plug in a semicolon to kind of just give a little bit of separation and say x equals 1. And this is going to tell me what is the value of the derivative at x equals 1. And that value is 22. Right? And that we could do, again, really simply with pen and paper. 18x plus 4. Well, if x is 1, that's just 18 plus 4 is 22. Right, so we're not gaining a lot from having the computer do question 1, nice and simple. Likewise for question 2, let's just go ahead and look at the plot. Over here, this becomes positive, this becomes minus 14x, this becomes a cubic function, negative 4x cubed minus 14x plus 20. So here's our shape. We've got kind of a zigzag shape. For this, this isn't explicitly an economics function. This is just a generic polynomial. So maybe we could have a demand curve that approximately fits this line. That would be sort of something we might do if we've got a bunch of data and we want to have a rough and ready estimate of what the demand curve is. Maybe we fit a polynomial and we find something that's good enough. But we're not worried about that right now. We're just doing a little bit of calculus. So with this, the derivative is easy. It becomes negative 12x squared minus 14. You plug in numbers, you're able to figure stuff out. So let's look at the more difficult ones. First off, we've got x to the 4 minus 3 times x cubed minus 2. take a look at the function first. And so here we can see this is a pretty weird looking function, and we've got this product rule thing, and we're going to have a even more complicated thing with question 5 where it becomes quotient rule. But having Wolfram do it, it becomes as simple as we put in the thing, we look at what it is just so that we make sure what we're seeing makes sense, and we just tell it, take the derivative, and it gives us a result. This should be the right result. So understanding what's going on, doing practice on pen and paper will make sure that you didn't accidentally put in some error that gives you the wrong result, right? It is possible to get the wrong result here. But if you do everything right, you get your result faster. So our derivative, x squared times 7x to the 4, right? That passes the smell test because we're going to have an x to the 7 term. So our expanded form, 7x to the 6, well, when we multiply x cubed times x to the 4, we're going to have x to the 7, and the derivative of that is going to be 7x to the 6, right, for just that one term. Let me show you what I mean. If we have this, we're going to get this 7x to the 6 term, because this is just x to the 7. And so our derivative, this passes the smell test, just seeing some part of this that definitely should be in there. We're going to have a minus 2 times x to the 4. That's going to give us this part. We're going to have a minus 3 times x squared, and that's going to give us this term here. Right? So if we were to expand this formula out, let's do this. We can just say simplify, or maybe we'll tell it expand. If simplify doesn't work, here we go, our expanded form. So the derivative of this is really easy. This is just a polynomial. For question 5, again, we could just simplify it, although it doesn't simplify quite as nicely. We're not able to avoid having to do the quotient rule. Personally, I like to avoid the quotient rule just because the order matters and it's easier to mess things up. As we showed in the videos before, we can go from quotient rule to the product rule using the chain rule, right? So we can kind of take a circuitous route to get where we want to go. But we don't even have to go that far if we have the computer doing the hard work for us. So when we differentiate this, this is the one for question 5, your answer should be either of these, right? Are these different? No, these are exactly the same. You could expand it out to here, but you really don't need to. But you're going to show your work, so if you start here and you expand to here and you mess something up along the way, but I see this, well, you're going to get the points anyways. So we've got a derivative. Oh, this is nice. Look at that. So we can then copy this out, copy out our results, and we can say, let's derive the second derivative. Let's see how it handles that f prime. Cool, it gives us the f double prime. Input interpretation, that makes sense. That is what we're looking for. And then we've got some alternate forms. So we've got, with and without parentheses, x to the 4 minus 3x cubed, right? This all looks good. We've got an expanded form. We've got all the stuff that we need. And then we can say, let's take this, take that plain text. Is that what we want? It's not really what we want. Okay, we can take the Wolfram language version. Let's take this. So here it is in Wolfram language. There's a layer here where you put in stuff. This website tries to convert it into Wolfram language, but this is what's going on under the hood. So let's plug this in with x equals 1. We'll get the sign of the second derivative, and that value is something. Why is this not giving me a specific answer? Oh, whatever. So let's go back to here. And then rather than make you watch me struggle with this and experiment to find stuff, we'll get the big answer and then we'll go from there. So we can see at x equals 1, the shape of this curve is very clearly a positive slope. So we expect a positive number when we ask what is the slope at 1. And it is very clearly getting steeper, becoming more positive. So that second derivative is going to be greater than 1. We don't even actually need to know what it is in this case. In this case, it's relatively simple to just get that by eye. But if x was right here, right, if 1 was right here, well, then things are different. It might not be so clear. Or we might run into discontinuities, and that's stuff that we would deal with in a proper calculus class, but we're being lazy economists. All right, so we've got this. Let's derive this. We'll get our first derivative. And then we'll say, what is x equals 1? I guess let's take this plain text, plug that in, and ask to evaluate that at x equals 1. Maybe this works. Input. Homogeneous equation. Oh, what was that? That was to the power of 2. Let's see if this will work for us. Our worst case scenario would be to just plug in 1s for all of these x's, which would be really annoying. But here it did it for us. We get a value of 4. So let's try one more thing. So if I say derive this and then evaluate at x equals 1, if this does what I want it to do, it's going to give me the second derivative value at x equals 1. No. So here's our first derivative. So let's just check the second derivative. And then we'll copy out text. All right, so grab this plain text. They're different orders, but they're giving us the same fundamental information. Evaluate at x equals 1. So we've got that second derivative. We plug in x equals 1, and that's going to give us what we really care about, which is the sign of the second derivative. So in this case, we've got a sign of, is right? Why is this being weird? X equals 1, expanded form. How did I get that before? Got this whole thing, evaluate at x equals 1. I think it worked here. Or do we need to put it in parentheses? I think that's what we're missing. So this, by the way, is sort of the process, a very normal process for dealing with a computer in a programming context. You're trying to get it to do hard work, but that itself is not always easy, which is why, automating and analysts and data scientists and programmers get paid the big bucks. So we put that in, we said evaluate at x equals 1, and it's still not doing what I want. So what I'll do is just, here's what I'm going to do. I'm just going to plug this into text editor. Control H is usually find and replace. We'll replace all of our x's with 1s, and we'll hit replace all. Is that right? X, 12x. Yeah, okay. That is fine. H, run it again. Now, if we copy this into here, let's see what we get. Cool. It evaluates it appropriately, and we get a positive 12. So for question 5, what's going on with the slope around x equals 1? Right at that point, we're at a point where we have a positive slope, and it's increasing at a rate of 12 rise over run. It gets 12 points steeper as x expands by 1. Right now, it's actually changing as we move along there, but at that point, our linear approximation for what's going on, the slope of the tangent is, not the slope of the tangent, but the slope of the tangent is increasing at a rate of 12. All right, so let's go ahead and stop there. So big lesson from this is we can take mathematical functions, we can put them into a computer, and if we do things right, we can get the computer to do the hard work for us. For the sorts of problems we're looking at, Wolfram Alpha really is good. You can mess things up. You do have to figure stuff out, so this is not necessarily something you want to figure out when time is of the essence. But if you can figure it out when things are moving slow, then maybe when you do it when you are on the clock, you can get to results faster. And hopefully, especially with complicated functions, as long as you get them in right, you can avoid making the silly mistakes that our human brains are likely to make. All right, so as usual, if you've got any questions, let me know in the usual places, and I will see you in the future.